Hi. Um, Good morning. I'm Ming Zeng, a PhD student from Carnegie Mellon. Today, it's my pleasure to talk about our work. It's about improving the demand prediction model for the bike sharing system by using the global features. Okay, here is the outline of my presentation. I will first talk about the background and the motivation, then introduce the related work briefly, and then I will talk about our proposed model and experimental results, and finally I will make a conclusion. Okay, here's the background of the application. It's for the New York City bike sharing system. The left-hand picture will give you how does bike station look like. There are some dots for the bikes, and the and the right picture shows the location of the bike stations in the New York City, part of New York City. This is the Manhattan area. And you can see that there are a lot of bike stations in the city, and the users will pick up the bike in one station. They may use for commute or taking a tour around the city or exercising, and they will drop off the bike in probably in different stations. So how to allocate those bikes, those resources to each station is a very challenging research. It's a very challenging question. To design a good rebalancing algorithm, we will first have a good prediction model for each bike station, because we know that for each bike station, their demands are usually different based on the usage. So if we have a good demand prediction model, the service provider can maintain the station facilities more efficiently. And also, that could help them develop rebalancing bike sharing algorithm smartly. And here are some most recent work. All of the works are about rebalancing optimization. But before that, they also do some demand prediction. Zeng and the other researchers use the linear regression with some weather features and row features to estimate the demand. And Mahoney, they use the average trip in the time window in the rush hour to build a prediction model. And Liu and the other researcher, and this is actually the KDD paper this year, and they use the weighted KNN to predict the pickup demand, and the arrival probability model to estimate the drop-off demand. Here in our work, we define the demand as the sum of the pickup and the drop-off. That is actually the number of visits for the station. We will use the regression-based model to build our prediction model. Okay. Then I will talk about the proposed model. Here are some of the features that we are using in our baseline, and also part of the features in our proposed approach. There are the day of week, and the month, and the temperature, and the weather condition. We can see that the demands are usually higher in the weekday than the weekend. And for the months, the fall season have the highest demand than the other seasons. For the temperature feature, if the temperatures are too extreme, like too hot or too cold, there are usually less demands. For the weather condition feature, the observation is consistent to our intuition, like less rain or snow, there will be more demands. Okay, here are the features, all the features that we use in our approach. Okay, then it's very straightforward to come up with the city-centric model, which is a single model for all the stations. It's very easy to understand, but there will be a very critical problem here because the features, the distributions of the features between the stations might be not the same. So let's take a closer look at the minimal temperature feature. We can see that the shape of blue stations and the red stations are different. The same thing happens in the minimal temperature between the other two stations. And we can take a look at the day of week feature. For the red station, it has the highest demand on Wednesday and the Thursday. On the contrary, for the blue station, it has lowest demand on those 2 days. The same observation also happens in the other two stations. So because of this inconsistency problem, building one model for the whole stations will have a low accuracy because of this problem. So we can use the alternative approach, which is called station-centric model, to capture the patterns for each station. And we will build the individual model for each station to avoid the feature distribution inconsistent problem. But there is another challenge. Here is the figure shows the accumulative number of new stations of last year. The x-axis is the number of days, and the y-axis is the accumulative number of new stations. We can see that for each month, there will be new stations. For the new stations, there are only little data for training. It's not enough to have a robust regression model. So we will think of the other way to achieve better performance. And then we propose the hybrid model, the station-centric model with global features. First of all, we will have the global feature extractor. Here we use the GBDT and the neural network as the global feature extractor. And these feature extractors are trained on the entire data set for the feature transformation. And for each station, we will still build an individual regression model for each station. But we will first input the original feature from the station and input them to the global feature extractor. Then we will get the new features. And then we will concatenate the new features to the original feature and build a regression model on top of it. And here, I also want to mention that this approach is similar to the pre-training for the neural network. For example, to train a neural network for the image recognition task, we will get benefits from pre-training the neural network on the external data like ImageNet. Then we applied this pre-trained neural network to the other task. Similar to that, for each station, the other entire data set is like external data. Then we will capture the global information from that, then we can get an improvement. And this is the intuition of our proposed approach. And here is the example. First of all, we will have a set of training data, xi to xn, denote the n stations. And we will train the neural network here. And we will take the last layer of the neural net as the new feature. And if we want to build a regression model for like station 1, we will input the station 1's feature to the already trained neural network, and we will get the neural network feature called the deep learning feature, and we concatenate those deep learning feature to the original X1 station feature, and then we will have the new feature space. Then we'll train the station-centric model on it. Okay, then the experiments. In the experimental section, we mainly answer these two questions. The first is, how is the performance of this hybrid approach? And the second is, in which scenario we should use this hybrid approach? I will first introduce the settings in the experiment. We'll use the data from last year, 2015, for training, and test our approach on the data from this year. At that time, we only have the 3 months of the data of this year, so we'll test our model. We test our model on the beginning of the 3 months. And for the evaluation metrics, we use the MAE, RMSE, and the RMSLE. It's very interesting to mention about the RMSLE feature. RMSLE metric is widely used in the Kaggle competition. The intuition here is that if the service provider wants to give more penalty to the under-predicted model, this is a good metric to evaluate that, because if the service provider may think of that, if they have the under-predicted result, not only the service provider will gain less profit, and also the users might complain because of the insufficient bias. That sometimes that will be even more harmful than the over-prediction. Okay, then here are the results. Actually, in our experiment, we ran 4 regression models there, and here we are showing the best of two of the best model, the linear regression and the random forest. We can see that for the last 3 columns are our proposed model with different combination, the GBDT, feature extractor, and the neural network, and the combination of them. They are most of the case perform the best, and we can see that the city-centric model performs the worst here. And this can indicate the advantages of our proposed model. The other experiment is carrying on the varying size of training data. The CC means the city-centric, SC means the station-centric based model. In most of the case, the station-centric model performs better. You can see the red line and the green line. It's very interesting to notice that when we have a relatively small size of the training data, like a 10% to 20%, the city-centric model performs the best. I think that's because even for the station-centric model, there are not sufficient data for them to train the robust model. So we can draw the conclusion that when you have a very small amount of training data, we better use the city-centric model for the regression. With the increasing number of the training data, we can use the proposed approach, the city-centric base with the station-centric base model with global information to build a prediction model. Then we go to the conclusion section. We build a station-centric model with the global features, and it has the lower error, and it can be successfully applied to the real-world application. For the future works, there are two directions. The first is, instead of building a station-centric model, we can put the similar stations together and to frame it as the location-centric model to avoid the insufficient training data problem. We can also create more features then we can get more benefits from those global feature extractors. Thank you very much.
Thank you for the talk. And you are doing the forecasting on the demand, so it's more like time series. They have lots of the autoregressive of terms, and you're using the regression, assuming this would not actually measure the regressive of the terms. Are you using a regressive model or just using the linear regression?
I also take the historical data from the last 2 weeks or last week to make the forecasting model. So I do take the.
No, I'm referring like a multivariate or like if you have to measure of this the forecast, your previous actual performance of your demand, and will be some of the variable as a feature to feed into your prediction as well, right? That's
yes.
the autoregressive,
yes.
the term.
Yes.
And also have the seasonality, assuming have have some of the fall festival or any events, those have some of the cyclic or some of the periodic of the pattern. So I'm just curious, this method comparing as the model this problem as a regression versus you model as a forecasting problem. I mean, in the time series analysis, they have lots of the method has been used.
Yes.
Have you think actually to extend it to actually compare the result, or you have done something in that area?
No, we haven't evaluated on the autoregressive model because I didn't embed the other information like the weather information into the autoregressive model. So we only take. So our base case is the model without external feature. So we only verify the adding external feature, external source information can improve the model.
Yeah, I think because typically this the seasonal or the some of the pattern would help you in improve the accuracy. I think that's
it's very interesting to mention that if we can build an autoregressive model as the baseline, and we can embed more features to the autoregressive model, and with the global feature, and hopefully we can see some improvements.
I think so, because you haven't actually done including that kind of because lots of the feature, typically the weekly, for example, weekend are definitely going to be much higher demand than the weekday, for example, if the tourists actually in town, for example. So those features cannot immediately from this independent feature or extracted auto extraction can be finding that easily. But that one can be based on the historical on the weekly pattern on your own time series. You can easily add in those kind of terms, I think.
Yes.
Your model does have a day per week or after that, right?
I have those features, but here, yes, F1 and F7, but.
So those will partially capture some of those seasonality that you mentioned?
Yeah, partially, but not the fully autoregressive model.
I'm wondering, how do you estimate demand in stations where demand has reached full capacity?
Actually, we didn't consider that. We assume that the true demand is the showing on the historical data. It's actually the number of visits, the sum of the the pickup and the drop off. If it's larger than the capacity, we didn't consider this case.
So if it is capacity, then your model is underestimating.
Yes, the model will be underestimated. Yeah.
I think we have time for a couple more questions.
Yes. A couple of questions. The first one is okay. So the first question is you showed that SC plus NN is used NN to generate new features.
Yep.
So what's the meaning for the station centralized plus the GBDT? Yes. What's that? It's used to generate new features, or what's the role of that term?
It's generated it will generate the new features in the not linear way. So you can also use PCA to generate new feature and catenate to the PCA feature to the original feature. But the PCA feature is still the linear combination of the original features. So what I prove here is the feature from the neural network and GBDT features are more powerful, and it can add some benefits to the prediction model.
Okay, I got it. So a short question for the. Right now, you utilize some global features and plug these features in the model to do some prediction.
Yes.
And have you guys ever considered like to build some sort of overall model or background model for all the station without enough data, and then do some comparison? For the station with enough data, okay, build a dedicated model for each station. But with all stations without enough data, can we use some global statistics or features to make some model do the prediction?
So your question is, for the station which has insufficient data, we can use the global feature to improve.
Sort of global features, yes. Some features, for example, like your statistics about the 7 days demand for the past 2 weeks and the temperature, historical information. I mean, use all the global statistics or feature based on the global data, and then use all the data to build a model for all the stations without sufficient data.
Yes, in that way we can get some improvements. But our human being cannot design all the features from the whole data set. So I'm hoping the neural network can extract the global features automatically to improve the results.
Okay, thanks.
So the obvious application of this to like a bike sharing program is to operationalize it and then say like, on day X, we need to have this many bicycles at this station. How is that impacted by the fact that like the demand amongst users is actually based upon the availability? Users will figure out that like, oh, this station almost is always out of bikes, so like I should go to a different station. And as you try to make changes to that, you're basically implementing a control problem. Did you guys look into that at all?
Not yet. I think this is a prior word to your question. If with the better prediction model, the service provider can have a better sense to understand the reason and what actually will happen in the future. Then they can have it can be served as for the rebalancing optimization problem, but we haven't looked into that. Thanks.
All right, one last question.
Thank you. Yeah, so my question is, currently we use the deep learning to get better features for those stations without many data. But what if we just do a very simple thing is, instead of training regression model independently for each station, we train the model jointly plus some like a high order group lasso or high order cluster lasso to give more information to those stations with missing data. So as a very illustrative example, if this station, I do not have many readings and many data about the past demanding, but what I know is that this station is very close to a CBD area, then I could use other stations also close to CBD area, and there are past historical data to provide better training model for this station.
Yes, this is what we are going to do. It's the location-centric model. We put the stations nearby each other together to train a location-centric model. So the stations can leverage their neighbor's information to improve their results, to improve the prediction.
But instead of just location, we could using more rich information. It's more like to influence the similarity between the stations and using that information to impute the missing values for those stations.
Yes, then we might probably need to build a similarity evaluation model, matching model on top of before that. Yes.
Thank you. Another question is that data open for academia to use? I mean, the interesting data set you used in your paper?
It's a public data set. Yeah, you can download it online.
Thank you.